So let's talk about the NVIDIA CUDA compiler. This is what you would actually use to compile CUDA C applications, but it's not really a compiler. It's more of a wrapper around your host compiler. And what NVCC does is it effectively splits your code into different parts for GPU and CPU execution. And naturally, you get lots of GPU specific settings in your project, some of which would be predefined by the project template that you originally chose. And then the process is simple. Your GPU code gets translated into yet another language called PTX, which in turn is converted into binary code by your graphics driver. So the whole point of NVCC is to hide all the compilation magic from developers, and the way it does it is by kind of mimicking the behavior of whatever underlying C++ compiler that you'd like to use. So behind the scenes, what NVCC does is actually a very complicated process. So here is a grossly oversimplified illustration. So you start with your file, or indeed a set of files, and they contain both the host code, so the code to run on the CPU, as well as the device code that you would run on the GPU. And the way that NVCC works is it effectively splits the source code into device and host parts. So here NVCC would separate this file into the part that has this global declaration, so that's something that it knows would run on the GPU, as well as the ordinary C++ code that would be run on the CPU. Now, the NVIDIA compiler continues to handle the device code, so it takes the device code and compiles it for the GPU, but the host code is actually passed to the host compiler. So in my case, that would be the Microsoft Visual C++ compiler. And then these two parts are simply combined and merged into a single executable. Now, I mentioned PTX briefly. So what is PTX? Well, essentially PTX is the assembly language of CUDA. It's something like the intermediate language in .NET or the bytecode in Java. PTX is essentially a set of low-level GPU instructions that the graphics driver can take and execute on a particular graphics device. And when working with CUDA C, you won't get to see much of it, but you can configure your project to output the generated PTX if for some reason you want to take a look at it. Now, PTX is probably of most use to compiler writers. So for example, if you've got a programming language and you want this language to support CUDA natively, you could cross-compile your language to PTX. And of course, there is a possibility of writing inline PTX right inside your CUDA C code, and this can be useful in the rare cases where you need some performance optimization.